physicist, Ofojebe Tochukwu Alex. Blind Nigerian physicist, Ofojebe Tochukwu Alex. And the topic we are treating today is equations of motion. Equations of motion. By equations of motion, we mean those equations that we use in solving problems that pertain to a linearly accelerated or linearly accelerating body. That is, body that is undergoing uniform acceleration. And in our last lesson, we defined motion, or we explained what motion is by saying that a body is in motion if its position changes with time. So when the position of a body changes with time, we say that the body is in motion. And one that is undergoing uniform acceleration is called linearly accelerated body. And such body, there are equations that we can use to calculate the distance of the body at any time, the distance of the body at any time. And these equations of motion relate distance to displacement, relate displacement to initial velocity, final velocity, acceleration, and time. So this relates, equations of motion relate displacement to initial velocity U, final velocity V, acceleration A, and the time T. And let's start from where we know very well. We're going to start from where we know very well. And that is the place we said in our last lesson that A equal to V minus U all over T. A equal to V minus U all over T. Meaning that acceleration, which is A, is equal to final velocity, which is V, minus initial velocity U all over time divided by time T. Now, if we cross multiply this equation, we are going to have V minus U equal to AT. By cross multiplication, we have V minus U equal to AT. And by carrying U to the other side of the equation, carrying it over the sign of equality, we have V equal to U plus AT. V equal to U plus AT. We can call it equation 1. V equal to U plus AT. Now, we knew from our last lesson, we can bring to our knowledge of in our last lesson, where we said that displacement is equal to average velocity times time. Displacement equal to average velocity times time. And we represent displacement with S, small letter S, and the average velocity as V plus U all over 2. Average velocity as V plus U all over 2. Because if you are finding the average of two things, you have to add them, their sum, and divide by 2. Then times T, which is time. So if we now combine the two equations, bring this equation together, we are going to have S equal to V plus U all over 2, bracket T outside the bracket, meaning that displacement is the product of average velocity and time. That gives us equation 2. So that one came from, we said displacement is equal to average velocity times time. And average velocity is V plus U all over 2. So if you now multiply by time, you get S equal to V plus U all over 2, bracket T. Now this is the second equation of motion. Then we now move to further. Suppose we substitute V equal to U. Suppose we substitute V equal to U plus AT. Suppose we substitute V equal to U plus AT in the second equation. We are going to get that S equal to, you open bracket, U plus AT plus U all over 2, bracket T. U plus AT plus U all over 2, bracket T. And that gives us S, because when we add U and U, we get 2U. And that gives us S equal to 2U plus AT all over 2, U bracket T, meaning multiplied by T. And when we remove the bracket, we have S equal to 2UT plus AT squared all over 2. 2UT plus AT squared all over 2. We can separate this equation into two fractions of the same denominator to have S equal to 2UT all over 2 plus AT squared all over 2. I repeat, S equal to 2UT all over 2 plus AT squared all over 2, which implies that S equal to 2 cancels 2, you have UT plus, since 2 cannot cancel AT, we have half AT squared. So we have S equal to UT plus half AT squared. This gives us the third equation of motion. This gives us the third equation of motion. Then we can move from here. Can you give this statement? Now let's substitute. Now let's substitute V equal to U plus. Now let's substitute. Can you hear them? Okay. From V equal to U plus AT, that's the first equation. From V equal to U plus AT, we can make U the subject of the formula to have U equal to V minus AT. If we make U the subject of the formula, we have U equal to V minus AT. If you substitute it in the second equation of motion, if you substitute it in the second equation of motion, so if you substitute it in the second equation of motion, we have that S equal to open bracket, we have that S equal to open bracket V plus V minus AT all over 2. You bracket it and write it outside. That is, we have S equal to V minus AT, V plus V minus AT all over 2. You bracket it, put T outside. Therefore, we have that S equal to 2V minus AT all over 2. S equal to 2V minus AT all over 2. You bracket it, T out with your T outside, multiplying T outside. So if we remove the bracket, we have that S equal to 2VT minus AT squared all over 2. S equal to 2VT minus AT squared all over 2. If you separate this equation into two fractions, if you separate this equation into two fractions of the same denominator, we have S equal to 2VT over 2 minus AT squared over 2. S equal to 2VT over 2 minus AT squared all over 2. And then, since 2 we cancel 2, we have VT. And 2 cannot cancel AT squared. We write it as half AT squared. So we come to, we have that S equal to VT minus half AT squared. Call it the fourth equation of motion. Call it the fourth equation of motion. Now from here, we can also move a step further. From here, we can move a step further by saying, since S equal to average velocity times time, since S equal to average velocity times time, now in equation 2, suppose we remove T and replace it with V minus U all over A. If you remove T and replace it with V minus U all over A, how did we get T equal to V minus U all over A? We go back to the original equation, that is A equal to V minus U all over T. That's equation for acceleration. A equal to V minus U all over T. And that gives you AT equal to V minus U. AT equal to V minus U. Therefore, T will be V minus U all over A. So T will be V minus U all over A. So we can substitute it in this second equation of motion to have S equal to, what is the name of it? To have S equal to, you open bracket, V plus U all over 2, you close bracket, open another bracket, V minus U all over A, meaning average velocity times time. The time has been replaced with V minus U all over A. Therefore, S will be equal to, our S will now be equal to the product of V plus U and V minus U all over 2A. Because when 2 multiplies A, you get 2A. So S will now be the product of V plus U and V minus U. And the product of V plus U and V minus U simply means you expand that equation. We expand it. We expand the numerator. Okay, so we start. So that is S equal to the product of V plus U and V minus U all over 2A. And you know that V plus U times V minus U, when we expand it, we have S equal to V squared minus UV plus UV minus U squared all over 2A. So we have S equal to V squared minus UV plus UV minus U squared all over 2A. And the UV plus UV minus UV will cancel, we give you 0. So what we now have is a 2AS by cross multiplication equal to V squared minus U squared. 2AS by cross multiplication equal to V squared minus U squared. So that gives us the fifth equation of motion. The next thing we are going to do now is, how do we use these equations of motion? How do we use these equations of motion? Remember, all these equations of motion, they have 4 variables. Each of them has 4 variables. The first equation, if you write it down, the first equation, which is V equal to U plus AT. V equal to U plus AT. There are 4 things there that you have as variables. V, U, A, and T. V, U, A, and T. Then the second equation of motion, that one that says S equal to V plus U all over 2 bracket T. Then the 2 variables are S, V, U, and T. S, V, U, and T. There are 4 also. Then when you go to the third equation of motion, which says S equal to UT plus half AT squared. The 4 variables here again are S, U, T, and A. S, U, T, and A. And the next equation, which says S equal to Vt minus half AT squared, the variables are S, U, T, and S, V, T, and A. S, V, T, and A. You see that all of them have 4 variables. All of them have 4 variables. Let's take up the last one, which is 2AS equal to V squared minus U squared. 2AS equal to V squared minus U squared. The 4 variables here are A, S, V, and U. A, S, V, and U. So each of them has 4 variables. And once we know 3 of them, any 3 of them, we can get the 4th one. So whenever we are choosing the equation we are going to use, we know the 3 things we are given. Then look for how it is related to that one you are looking for. So that is the equation you are going to use. Okay, so let's go to one question, one example, after which we go to another one. This one goes like this. Okay. Now let's look at the solution to that question. That's example number 1. Let's look at the solution. Now, from the question now, U equal to 0. U equal to 0 because initial velocity is 0. The initial speed is 0 because it started from rest. When something starts from rest, then the initial speed or velocity is 0. Then the next thing is that its acceleration is 2 meters per second squared. Its acceleration A equal to 2 meters per second squared because acceleration has unit of meter per second squared and it is the rate of increase in velocity with time. You know, speed and velocity has the same concept. The only difference is that while speed has no direction, velocity has direction. So when it comes to calculation, I'll be using them interchangeably. When it comes to their magnitude, they are the same thing. But what differs is that one has direction, which is velocity, while speed has no direction. But when it comes to calculation, I can always use them the same way. Now, t here is half a minute. The time here is half a minute. So t is equal to 30 seconds. T equal to 30 seconds. Of course, we know that half minute is 30 seconds. Then, the first equation here, it says, calculate the maximum velocity. It says, calculate the maximum speed attained by the car or the particle. So what we have here is V equal to U plus AT, because it's the formula that has all the three things we are given. V equal to U plus AT. Therefore, V equal to 0 meter per second, V equal to 0 meter per second plus open bracket 2 meter per second squared times 30 seconds. You close the bracket. I repeat, V equal to 0 meter per second plus open bracket 2 meter per second squared times 30 seconds. You close the bracket. Therefore, V equal to, that is the maximum or the final velocity attained by this particle, equal to 0 meter per second plus 60 meter per second. 0 meter per second plus 60 meter per second. And that gives you 60 meter per second. So the maximum speed attained by this particle is 60 meters per second. Okay, that is the maximum velocity. Then II is looking for the distance it covers during this the time of acceleration. The distance covered by this particle during this time of acceleration. So we can now use the second equation of motion or any other one, because once we have worked one question, then the next question we can apply any of those equations. So we write S equal to the second equation, S equal to, you open bracket, V plus U all over 2 bracket T. We are looking for distance or displacement covered during that time. So when it comes to calculation, we can also use distance and displacement interchangeably. So S equal to open bracket V plus U all over 2 bracket T. Therefore, S equal to, our final velocity we got from the first equation, or the maximum speed we got, is what? It's a 60 meter per second plus our initial speed is a 0 meter per second all over 2. You close bracket, and after the bracket we write 30 seconds. After the bracket we write 30 seconds. That gives me S equal to 60 meter per second all over 2. You close bracket, then write 30 seconds outside the bracket, meaning multiply by 30 seconds. So 2 cancels 2 to give 1, 2 cancels 60 to get 30. So we have S equal to 30 meter per second times 30 seconds. S equal to 30 meter per second times 30 seconds. Therefore, S equal to 900 meters. So the distance covered is 900 meters. So simple. Okay, so that's one. Okay, then let's have the second example.
Example 2. A car moving with a velocity of 30 seconds increases its velocity uniformly to 60 seconds within the time of
60 meters per second.
All right, 60 meters per second within the time of 1/4 minute. Calculate I, its acceleration. I, the distance it covers within the time given.
Repeat it.
Example 2. A car moving with a velocity of 30 meters per second increases its velocity uniformly to 60 meters per second within the time of 1/4 minute. Calculate I, its acceleration. I, the distance it covers within the given time.
So you see, in the first question we solved, we were given the initial speed because the car started from rest. We were also given the time interval as well as acceleration. Then this one, the three things we are given here are different. We are given the initial velocity, which is 40 meters per second. Then we are given the final velocity, that's after the acceleration, which is 60 meters per second. And the time, then we are required to find acceleration. So it's a little deviation from difference from what we had before. So we are going to see how we are going to look at this question. Okay. And here is the solution to the second equation. Here is the solution to the second problem. So here, that's the initial velocity equal to 40 meters per second. 30 meters per second. 30 meters per second. Then the final velocity V equal to 60 meters per second. The final velocity V equal to 60 meters per second. And the time t, the time for this motion is t equal to 1 minute, which is equal to 60 minutes plus 60 minutes plus 15 seconds. 60 seconds plus 15 seconds. Remember, 1 minute is 60 seconds, and 1/4 minute is 1/4 times 60. That gives you 15 seconds. So 60 seconds plus 15 seconds, which is equal to 75 seconds. Then we now write A equal to question mark. We are looking for acceleration. A equal to question mark. So the formula that will connect this is our original formula. That's the original equation. A equal to V minus U all over T. A equal to V minus U all over T, which gives us A equal to 60 meters per second minus 30 meters per second all over 75 seconds. 60 meters per second minus 30 meters per second all over 75 seconds, which gives us 30 meters per second. That is equal to 30 meters per second all over 75 seconds. I repeat, 30 meters per second all over 75 seconds. And that gives us 0.4 meter per second squared. 0.4 meter per second squared. So this is the answer to this, the first part of this question. Then the second part of this question says we should calculate the distance covered during this. We can still use the equation 2 that we used in the first one. But just as I told you, if you have used one of the equations of motion to solve one question, to solve a question following it, you can use any of the two. Close your eyes and use any of the other equations. So in this case, let us apply S equal to ut plus half at squared. Instead of using the same S equal to V, our u is 30. So we have 30 per second times 75 seconds, close the bracket, plus you open another bracket, 1/2 times 0.4 meters per second squared all over 1 times 75 seconds times 75 seconds all over 1. You close the bracket. I repeat, S equal to, open bracket, 30 meters per second times 75 seconds, that's u times t, you close the bracket, plus you open another bracket, half times 0.4 meter per second squared over 1 times 75 seconds times 75 seconds all over 1. You close bracket because time it is t squared. T squared means you have to multiply 75 meter per second times 75 meters per second. So in the next line now we have S equal to 2250 meters. That is 30 times 75 gives you 2250 meters plus 1125 meters. 1125 meters. How did we get that? That we multiply everything, half times 0.4 meter per second squared times 75 seconds times 75. We get that value. And that gives me 3375 meters. That is 3,375 meters. That's the distance covered within the time. Okay, so that one is okay. Then we are now moving to example 3. Now let's have example number 3.
Example 3. A train undergoing uniform retardation passes 3 points A, B, C that are in a straight line. Its velocities at these points are 162 km per hour, 126 km per hour, and 54 km per hour respectively. If the distance from B to C is 80 meters, calculate the distance from A to B.
Repeat the question.
A train undergoing uniform retardation passes 3 points A, B, C.
So A, B, and C are on a straight line. Which are on a straight line?
Yes, that are on a straight line.
Yes.
Its velocities at these points are 162 km per hour, 126 km per hour, and 54 km per hour.
So at the point of passing these points, the velocity of the train was found to be, the first one is 162 km per hour. At B, it was 126 km per hour, and at C, it was 54 km per hour. Continue.
Respectively. If the distance from B to C is 80 meters,
so the distance from B to C is 80 kilometers. 80 meters.
Yes. Calculate the distance from A to B.
Calculate the distance from A to B. So